globe. And she came back and she is currently a postdoctoral researcher at the University of Amsterdam, and her research recently has focused on routing algorithms for dynamic networks. And she's going to tell us about the spread of epidemic disease on networks.
Yes, so I actually changed the title to the spread of infectious diseases on networks. I'm very happy to be here tonight, and thank you all for attending. So let's get started. I want to start with quite a. Can you hear me with this one as well? Is it on? Yeah. With quite a pretty graph. No. I want to start with quite a nice visualization of perhaps not such a nice topic. So this bubble chart shows you the causes of death, the main causes of death during the 20th century. And the big red bubbles, so these ones, they correspond to the main categories. And then the orange ones are subcategories, they're linked to their main category. And the yellow ones are again subcategories of those. And as you can see, the biggest killer of the 20th century was non-transferable diseases. So this includes the biggest one, the biggest subcategory was cardiovascular diseases, including strokes. And then cancer actually got its own category because there were so many people who died from it. But the topic of today's talk is infectious diseases, which is also a really large fraction of the causes of death during the 20th century. And perhaps it's surprising to see that war, even though it's horrible, it's only really a small killer in the grand scheme of things. And as Frank said, I've lived in Australia, and then it's somewhat comforting that only jellyfish and snakes and crocodiles only make up this very small fraction of death. So infectious diseases. So there's actually two properties of infectious disease that make them very interesting to study and also quite scary in a way. The first is that they can appear quite suddenly and spread rapidly, like a natural disaster can too. But a natural disaster is normally localized. Normally, like an earthquake only affects people who live in that area. But with infectious diseases, they can actually spread to quite a large part of the population. And the biggest example of this in history occurred just as World War I was finishing, and it killed killed approximately 3 to 5% of the world population. It's known as the Spanish flu, and it killed more people than were killed in the war itself. And actually, one of the reasons that this may have spread so well is ironically the end of the war, when soldiers were returning and people were welcoming them home, and there were large gatherings of people, which makes it a really good way for a disease to actually spread. So I think we have all heard about the Ebola outbreak more recently, in 2014 to 2016, and even it was in the news again quite recently. And the main outbreak here was in Africa, and it actually killed more than 10,000 people. But there are also isolated cases in Europe and in the USA. And if we look at the picture on the right, this is not so surprising. Perhaps it's surprising that there wasn't more, because those are all the flights connecting people around the globe. And as you can see, our current society is very connected. And this is a relatively new phenomenon. People have never traveled as much and as far as they do now. So that leads us to two questions that I want to address in this talk. First one is rather scary. What would happen if a virus as deadly and contagious as the Spanish flu would appear today? And the second one is a bit more optimistic and perhaps more important. So I have a cough, but don't worry, you're quite far away. So in case of an outbreak, what can we do to reduce the number of cases? And so today's talk, of course, we're going to look at these questions from a networks perspective. And we're going to look at mathematical modeling, computational prediction, and vaccination strategies. So we start with, actually this mathematical model does not include networks yet, but we'll get there. we start with a classical model, and the reason I'm showing it to you is that it's quite simple, but it already illustrates some of the insights you can get from mathematical models. It's called the SAR model, after the three categories that you divide your population into. So the S stands for susceptible people, people who can contract the disease. The I stands for infected people, people who have the disease and who can spread it, who can infect others. And then the R stands for recovered, and those are the people who are no longer infectious, so they can't spread the disease anymore. And this can either correspond to lifelong immunity for a disease, or it could actually just mean that the people have died and they're not capable of spreading it anymore. So recovered is quite an optimistic term, but it's not necessarily a positive thing. And so this model only has two parameters. We have beta, which is the rate at which infected people infect susceptible people. So it's the rate at which people from the susceptible category move to the infected category. And then we have gamma, which is the rate of recovery, and it's the rate at which people from the infected category move to the recovered category. And the interesting thing that I want to show you about this is that the average behavior of this model can be classified into two different types of behavior. So these plots, they show you the progression of the diseases. On the x-axis, we have time, and on the y-axis, we see the number of people in the three different categories. So on the left, we're in not such a good space. We start with almost everybody susceptible. That's actually the same in both cases, and a few infected people. But here, the number of infected people grows, and then after a while, it starts reducing. But the reason that it starts reducing is that there's actually nobody really left to infect anymore, because the susceptible population is very small now. And at the end of this simulation, or at the end of this run of the epidemic, we see that almost everybody is in the recovered category, which is not necessarily a good thing. They may have died. In this situation, it's looking much brighter, right? Almost everybody is still susceptible, and there's a few people who have who've had the disease. And the difference is the parameters, beta and gamma. So, yeah. So we actually find, when we analyze this model, that there is something called the epidemic threshold, and you can express it in terms of this number called R0. And R0 is defined as the expected number of people infected by a single infected person. So for instance, for Ebola, this is roughly 2. So every person who gets infected, on average, infects 2 other people. For the Spanish flu, it was roughly 2.5. And for measles, it's as high as 8, and that's actually quite a moderate estimate. Now, it's perhaps not hard to imagine that the higher this number R0, the faster a disease spreads, and the more people will get sick. And in fact, this epidemic threshold lies exactly at the value R0 equals 1. So if R0 is smaller than 1, the disease dies out. But if it's larger than 1, then we expect the disease to spread. And this is not so strange, because for a disease to be able to spread, every person needs to infect at least one other person. And if we analyze the SAR model, we find that R0 can actually be expressed, in this case, as beta over gamma. And there's a lot of research going into figuring out what these values are. So how do we know what at what rate people infect other people? Well, we have to know a lot of things, like what is the contact rate, what is the mode of transmission, and how infectious is the disease. That's quite important research being done into figuring out how dangerous a disease really is. But we're talking about networks tonight. So now I want to talk about the same situation, but from a network's perspective. And one thing that I didn't mention explicitly, but which is the case, is that the SAR model assumes that the probability for a person to infect somebody else is equal for all pairs of people. So let's call this probability P. In case of a network, it looks like this. There's an infected person, and say there's just 5 other people in the network. Then the probability of infecting them is equal for all of them. That's the assumption. So let's see what happens. We'll just flip a coin, an unfair coin. It lands on tails with probability P, and then the disease is transmitted. If it lands on heads, there's no transmission. So let's see, there's the gilder. We flip, we get heads, there's no transmission. Flip again, heads again, no transmission. I don't know what I did, but okay, it's on automatic. But you can see what's happening, right? Tails, we transmit the disease to this person. Heads, we don't transmit, and tails, we transmit. And now we can repeat the same thing for these nodes. We can flip coins with probability P to see if the disease is transmitted. And in the end, we'll have a small network, and all the nodes that are connected by a path to the initial infection will be infected in the end. But of course, we don't really have to flip those coins at the time that a node is infected. We can do that beforehand. So this is exactly the Erdős-Rényi network that was mentioned by Nelly. These are Paul Erdős and Alfred Rényi. They're Hungarian mathematicians who came up with this random network model. And the idea is that you have a number of nodes, and each node is connected with a certain fixed probability P. And to get an instance of this network, you just flip enough coins so that you know whether these edges exist or not. And here are, for instance, 4 instances. For the value P is 1/2, so we're flipping with a fair coin now. And for our purposes, the main importance here is that some of these networks, they are connected. And so when one person gets infected, everybody will get infected in the end, in this world. And here, if this person gets infected, then there's only one infected case, and the rest doesn't get infected because there's no paths between the two. But if the infection starts here, well, it's still not so good. 5 people get infected, but 1 is not infected. So for us, it's very important how many components there are. But of course, we're not really interested in single instances of these Erdős-Rényi random graphs. We want to know this probability P, and then we want to say something about the expected and average properties. So how many edges do we expect could be a very mathematical question to ask about this model for a certain value of NMP, a number of nodes and probability. Or how many components do we expect, which is very important from the disease modeling perspective, because this means how many isolated islands basically are there in the population where the disease can be trapped. And what is the expected size of these components? This corresponds to the size of the outbreak in this model. And what is the probability that there's just one single component and everybody gets sick? And actually these networks are mathematically really well understood. And it turns out they have a similar threshold as we have seen for the SIR model, which is pretty cool because the mathematics behind them is quite different. But we still see this similar behavior where if P, the probability, times n, the number of nodes, is smaller than 1, then the network consists of many small components. So the network looks something like this, and the disease can't spread. Whereas if P times n is larger than 1, the network is likely to have a giant component which contains a substantial fraction of the nodes, which is bad news for a disease that runs on the network, or for us, maybe not for the disease. Because if it looks more like this, and one of these nodes gets infected, then all these nodes will get infected in the end. And so, this is different Erdős-Rényi networks for different value or increasing values of P. However, as Nelly has told you before, real networks don't really look like that. And it's quite clear that it's not that the probability of passing on a disease is not equal for all pairs of people. For instance, we see our family, our friends, and our colleagues much more often than other people. Also, I think the most obvious type of disease is transmittable diseases for which it's clear that the probability of infecting another individual are different for different pairs of individuals is sexually transmittable diseases. Of course, there needs to be some sort of relation for this disease to spread. And so current research is asking very similar questions as we have asked about Erdős-Rényi networks, but about networks with different structure. So if in this network, not all nodes have a probability of connecting, but if the nodes that do have probability of connecting or transmitting the disease have the same probability P of transmitting this disease, is there then also still a threshold, an epidemic threshold? And what is this threshold? And actually several researchers within this networks consortium that Frank was mentioning at the start of the evening are working on this topic. It's called percolation theory, and it's both has applications, but it's also very beautiful mathematics. So, and you do get some results, but sometimes when models get more complicated, we can actually no longer expect to compute or calculate exact results. And instead we use computational techniques. And actually here networks really give us an advantage over this traditional SAR model because we can put in different connections, but we still, we can't give you exact answers, but we just run simulations over and over again, and then we compute an estimate of the average. And I want to show you a short movie of how network science can help, and how it now has, in combination with large data sets, has quite reasonable predictive power. And I want to let Professor Alessandro Vespignani from Northeastern University talk for me, so I hope that the movie can be played.
We do this scientific work because we want to go into uncharted water. This is the sense of adventure. Humans are the carriers that transport diseases. Everything we touch provides an opportunity for the pathogen to spread from one person to another. Our daily interactions form the social network along which germs travel. But imagine if we could use that social network to predict the path of a virus before it travels around the globe. Then perhaps the germ you carry to get your morning coffee won't lead to an outbreak, because you'll know when to be ready for it. The way we can look at the world is we think in terms of networks now. Everything basically that we have built around us is a network. When you have such an awareness, you can really think about changing the world around you. One of the things that we really want to achieve is predictive power to track diseases and then develop models that allow us to forecast their evolution across the world. We integrate entire databases on human mobility, census data on where people live, geographically located, and that's create a kind of synthetic world in the computer. From this synthetic world in the computer, we run numerical simulations that forecast what and how and when the epidemic will spread around the world. You have to hand out those forecasts and scenarios to policymakers, and then they have to factor many things. You can tell hospitals this is the time that you have to postpone anything that can be routinely postponed, and that intensive care units must be free because you might face a wave of sick people needing attention. We can all think back to the H1N1 epidemic of 2009. That was the first time we were in a position to do a real-time exercise. And what we were able to predict, according to our data, was that the flu was going to peak in October, November, which is about 4 months earlier than the flu usually peaks. So we can do a validation of those results, and those results were mostly correct by the week. Now we can see that our computational models, the data that we integrate and the knowledge that we have accumulated on the spreading of diseases is finally being recognized for achieving predictive powers. At this moment, what we have here at Northeastern is a concentration of the most prominent people in the field. This is where things are happening. And somehow, what I feel is that we are living some kind of a revolution. So network science, data science, what we have at the moment is something that allows us to do incredible progress in an area that was not even possible to define 10 years ago. That's really like being in the right spot at the right time. It's amazing.
This video really nicely illustrates the power of computational aspects of network science. And so far I've just been talking about understanding network or understanding phenomena in disease spreading and predicting the spread of disease. But of course it's also one of the main questions is what can we do when there actually is an outbreak? And to tell you about this, I'm going to talk about vaccinations. And you've probably heard about herd immunity. So what is herd immunity? This is a level of vaccinations within the population such that it's unlikely for a disease to spread. And this actually only works in our old model, the SIR model and the eradication model, where we assume that everybody can infect everybody else. And recall that if this R naught, the rate that, or the average number of infections caused by a single infection, if this was larger than 1, then a disease is expected to spread through the population. So in this image, R naught is actually 3. And it's perhaps not so surprising that we have to vaccinate 2 people in order for R naught to become 1 or less. And in general, the rate of people that needs to be vaccinated is the R naught minus 1, so R naught minus 1 over R naught. And for Ebola, so we find the higher R naught, the higher the vaccination rate needed to require herd or to obtain herd immunity. For Ebola, this is 50%. For Spanish flu, it's roughly 60%, and for measles, it's as high as 78.5%. However, we also discussed that this assumption was not really, didn't really hold up. And in case, when we're looking at realistic networks in the context between people, this vaccination rate is no longer so useful, because it actually matters who we vaccinate, not just how many people we vaccinate. And in this very, very small example of a network, we can illustrate this by the ideas also that Nelly was talking about. If we vaccinate somebody at the periphery, the network hardly changes, right? We just save this one person from getting the disease. But if we vaccinate central people, then the network falls apart. And this is of course an exaggeration, but in a real network, it's also important to find those important people who are spreading the disease, who contribute much more to the spread of the disease, so that are central in the network. And vaccinate them, and not just randomly select people. But then there's another problem, because often we don't actually know the network on which the disease spreads. For instance, this morning I took the metro, and normally I ride my bike, so that corresponds to a different network. I could have infected all those poor people in the carriage with me. Whereas if I had chosen to ride my bike, I wouldn't have. So what do we do if we do not know the network of people? Well, then we use the following paradox, which is called the friendship paradox. And the paradox states, it's a little bit sad that our friends have more friends than we do, on average. And you may have always expected this, or you might be really shocked to hear it. But on average, this is true. And we can use this paradox to find popular people, and to find people who have many friends or many neighbors. So how does it actually work? If we select an arbitrary person and count the number of contacts they have, in this case 3, and then we select one of their contacts and count their friends, then on average this number will be higher. And at first this sounds paradoxical, but if we think about it a bit better, it's actually not so surprising, because this popular friend will be mentioned by many people as a friend, just because the person is popular. So the number of connections this person has counts towards many of the average's number of friends, increasing the overall average. So in fact, it's not so surprising that your friends have more friends than you do, on average. And how can we use this in vaccinations? Well, instead of vaccinating people at random in the population, we can take a random sample, so say we select this node at random, but we do not vaccinate this person. We ask them about their friends. Who are your friends? And then we randomly select the person. And now we're likely to find somebody who has more friends, and hence is a bigger spreader, more important spreader in the network, and we vaccinate them. So this is a nice way in which quite a simple mathematical paradox can help us improve our efficiency of our vaccinations. And I want to finish off on a happy note, because I hope I haven't worried you too much about all these infectious diseases. So just keep calm, love mathematics, and figure out a way to fight epidemic or infectious diseases. Thank you.